Hello. In today's Principles of Computer Security lesson, we are going to be looking at some other public key crypto systems. In the previous lessons, we have looked at a number of public key crypto systems. We have looked at RSA, and also we have looked at symmetric key in cryptography as well. So today we will look at two different mechanisms, crypto systems, that are relevant to many public key crypto systems. The first one that we are going to be looking at is known as Diffie-Hellman key exchange. So when we are continuing our discussion into public key crypto systems, we will start with Diffie-Hellman because it is one of the earliest examples where the main purpose of Diffie-Hellman is having a common shared secret key by two entities so that they can have secure communication. In a way, this is very common and very prevalent that any of you doing any communication online, any of your applications connecting to online servers, you are connecting to secure websites, in all of these situations, there will be a Diffie-Hellman key exchange happening. So both the entities will exchange some information whereby they arrive at a common secret key that they can use for communication. So, in a way, this is one of the first public key type schemes proposed. This was originally published by Diffie-Hellman in 1976, but the same mechanisms were well known in the secret community or in the governments as a secret project even before that, but it was kept secret and only declassified in 1987. So in a way, the publicly it first became available in 1976 as Diffie-Hellman, but a similar approach has existed before. So here what we are trying to do is we are going to have a way of exchanging a secret key. So our main intention here is exchange of a secret key, a public exchange of a secret key. So that's what we are trying to mainly achieve with Diffie-Hellman. So, and as I said, this is one of the most commonly used approaches that we would see even with many of the applications that we use today. Many of the online applications, many mobile applications, all of these, when there is a communication happening with a server and so on, this is something that may happen in the background. And one of the reasons why we use Diffie-Hellman key exchanges, it is a way for us to establish that the two parties in a communication have the same key. So the basic idea here is, if let's say if we have two entities, we have A and B, Alice and Bob are the two entities, and if they need to communicate with each other, they need to have some shared secret. But sending that shared secret cannot be done securely because there is no secure mechanism there. So because the need for that shared secret is to establish a secure communication channel. So there is no pre-existing way of sending that shared key previously. So this is where we come to use Diffie-Hellman key exchanges. So with this Diffie-Hellman key exchange, what we are trying to do is having a shared key, but what we will actually do is we will not actually exchange messages because exchanging messages cannot be secure, so we cannot do that. But what we would do is we would establish a common key. So that is, both parties are able to calculate using some mathematics, are able to calculate the same key. So both of them have the same key at the end, so they can use that for their secure communication. So that commonly calculated key will only be known by the two participants. So that is the main idea behind Diffie-Hellman. So that is, when we have, say, two parties, we will, each party will calculate a common key, and once we have a common key, we can establish a secure communication. So the value of the key that we would calculate will depend on some private information that each party would have. So each party would have some private information. So each party can have some private information, and then there can be some public information. So a combination of these will be used to create this shared common key. We will not go into the mathematics of this approach very much because that is not the main focus for us in this course. But I will share some additional materials that you can refer to get a better understanding of these things. So what we have is, we should start with a shared public information. So there should be some parameters that everybody agrees. So we would call them some global parameters. So we would identify a large prime integer or a polynomial. So that is something that we would identify first. Then we would also identify A, which is a primitive root mod of Q. Again, as I said, the mathematics is not pretty key for you all in this situation. So now what they can do is, what each entity can do is, based on this public information that they have, they can generate their own keys. Each entity can generate a public key. So each entity will create a public key. So we have some shared parameters. With that shared parameters, each entity is going to calculate a public key. So what we are going to do is, say we have A, there is a shared parameter that is known to A and B, both of them know that, and now both of them can use that to calculate a public key for each of them. So each entity will calculate this public key first. Then this public key will be using this shared information. Then after that, each of them can use, because that public key can be exchanged. So this public key can be exchanged with each other. So now A and B, if we take A and B now, A has YB and B has YA. Each other's public key is now available. Now, using these two keys in conjunction with the information that they already have, they can calculate the shared secret. So that shared secret can be calculated using this information, because we have the same information at both ends. We have calculated the keys with the same manner. So it will happen, the inverse or the opposite action will happen at both ends. So both of them will have the same keys. So then now this KB can be used as a private encryption key for communication between A and B. So when A and B are communicating, they can establish similar keys at different times, and they can keep on using that. So the attacker will not be able to identify what is happening at both ends, because the attacker doesn't know what the local calculation has been at the each of the ends, because the each entity was choosing their own secret at their side. So A would choose their own secret, XA, and B would choose XB. So now that XA and XB are not known to anyone, that is kept secret. This YA is only shared, and using YA and, or rather YB and XA is what we get the KAB. So that is the common key. So if I draw that again, so we have A and we have B. So first, there is a common parameter that we would use that is known to both entities, and using that, A would compute a private, each entities would generate a private, then each would generate a public, and this public will be exchanged, the public key will be exchanged. So now both sides know each other's public keys. Now what can happen is a combination of this private and this public can be used to generate, and this private and this public, that combination can be used to generate, and they both would generate the same key, the same shared secret key. So this is what we would keep as the secret there. So that is the very basic of Diffie-Hellman. So if we look at this with a simpler example here, what you can see here is, so Alice and Bob needs to exchange keys. So they would agree upon, so normally when we say they would agree upon, either everybody will agree upon a particular protocol may or like a mechanism would identify a predefined value as this prime, so that it can be something predefined there. So these values will be agreed upon by both ends. So then A will select a secret key on its own, not known to B or not known to anyone, only A would know this. And B would select a secret key, again only B would know that. Then A would compute their own public key and share that with Alice. So this is what Alice is going to receive. Similarly, B would compute a public and they would share that. Now, if we put that with the shared information, if we create the shared session key, what we would be resulting in is the same value. So we would have the same value there. So that is what we try to achieve in these key exchanges. We arrive at the same values there. So it is a shared key value between both entities. So that is the main idea behind Diffie-Hellman. So the main purpose of this type of key exchange protocol is that users can create their own private keys and establish or create shared private keys and establish secure communication while still not having the need to communicate that secret key over unsecure channels. So the problem that we have is when we have two entities and when these two entities currently don't have a secure channel for communication, that is where we can use this type of an approach where both parties are independently calculating using some common information and some shared information, but the finally computed key is only known to these two entities. Anyone else will not know because that key also includes some private information. Some private information that is only known to the both entities. So this is the main sort of idea behind key exchange protocols. But one of the problems is if we have a man in the middle attack, then this might as well fail. So, for example, if we think about a man in the middle attack, say if we have A and B trying to communicate, and there is another entity in middle that is trying to intercept. So what can happen is when A tries to send the public key to B, it may be received by D and it may send its own one over there, and this man in the middle can establish two separate secure channels with both the entities, and all these communication will happen through the man in the middle, and man in the middle will have the ability to intercept, decrypt and re-encrypt and forward messages. So they can stay in between that. So that is one of the problems that we may encounter if we are using this approach. So we would still need some authentication mechanisms, but generally this is a key exchange is one of the approaches that we would still use. So the next topic that we are going to discuss today is known as LGAML cryptography. So when we talk about LGAML is another public key cipher system. So similar to RSA, or rather, it is another alternative to RSA. So one of the main reasons why we look at LGAML is to understand that RSA is not the only public key system that we would use. LGAML is also there. And particularly one of the main differences is that LGAML is based on a different one-way function. So it is not RSA, so it uses a different one-way function. And we may come to look at that LGAML is the basis for many sort of different cryptographic applications. So that is also a reason why we may look at LGAML. So let's just briefly go through LGAML again with some examples to understand how it can be established. So these are some simple examples. So we would start with a large prime number P. So that is what we would start with, and we would select a special number G. So this G must be a primitive element of modulo P. Then we will choose a private key X. So again, X can be anything larger than 1 and smaller than P minus 1. So these are three numbers that we would come up with. So with these three numbers, X, P and G, we would try to compute the public key y. So the private key is something that we choose, and with the combination of these other two values, we will calculate the public key y as g raised to the power of private key and modulo p. So this is what we would get as the private key, or rather public key. So if we look at that with an example, if we select p as 23, then we will select a primitive element g as 11. We can choose a key as 6, and then we can compute the public key as 9. So here our public key is 9, private key is 6. So these are the two information that we would have there. So when we think about encryption, we normally encrypt that with the public key. So encryption would be happening with the public key. So if we have a plain text that we want to encrypt, we would encrypt that using this mechanism. So again, if we look at that with an example, so if our message is 10, so that is the message that we want to encrypt. So then public key is something that we know. Then we can generate a random number there, and we can produce the ciphertext as a pair of two different values, because like using the two approaches we would because like we have two ciphertexts because C1 and C2 computed slightly differently. So C1 is G to the power K and mod P. This one is message into Y to the power K and mod P. So here is where we consider the message there. So we would calculate that using the public key there. Public key is 9, and we would calculate C1 and C2. And our ciphertext is the combination of both of these, C1 and C2. So now when we think about decrypting this message, we can think about how we can use the private key now, because in the case of encryption we are using the public key. Now we are going to use the private key. So what we are going to receive as C1 and C2 are these two. So these are the two values that we are going to receive as C1 and C2. So the way that we would generate the actual message is by calculating sort of the inverse function of that. So we would compute, we would try to compute or resolve using these two, understanding of these two equations and understanding of our private key, we would be able to generate M. So using this equation. So again, if we look at this example, this is what we will receive as our secret key, or rather ciphertext. So then we can do these two computations, C1 to the power x, and this, that is 1, and then C2 divided by yk, and this, that is the second one. So if we put that into those two equations, we can come back to the plain text as 10. So that is what we were trying to compute there. So if we think about the security of LGMO, you may recall, like when we were talking about RSA, that we sort of briefly mentioned that there are how we can go about trying to decrypt a ciphertext without the knowledge of the private key, and also trying to determining the private key. So similar sort of issues you may come across when you think about LGAML as well. So I would suggest as a self-study exercise that you go and read about this LGAML in a bit further and sort of the security implications there, and see whether and how this can be broken, or what are sort of the challenges in not being able to do that. So there are sort of, when we talk about LGAML and RSA, there are different reasons why we may use one or the other. So, for example, LGAML doesn't require factorization. Being hard, it doesn't require hard factorization as the underlying mathematics, whereas it requires a random number generator. And as you know, random number generators can be a problematic thing in systems, and also it requires message expansion. So again, this is also something that you can look up a bit more, and I will also share some interesting materials along with this lesson for your benefit. So what we wanted to discuss today is mainly sort of expanding on our previous discussion about public key systems, and talking about how in practice that we may use public key systems. So when we think about the public key systems that came about in the 70s, they had a lot of advantages why we wanted to use public key systems, and they have become more and more important in the recent times as we go about using these. So when we think about online-based systems, when we think about many of the web services and so on, public key systems are one of the basics how we go about securing these systems. So that doesn't mean that everything is going to be based on public key systems. As we said, things like Diffie-Hellman are still being used to exchange and establish a symmetric key, because in Diffie-Hellman what we are establishing is two shared secrets at both ends, whereby we can have symmetric key encryption. So, but we can use public key on top of Diffie-Hellman as a part of authentication, because in a way of avoiding a man in the middle and things like that, and different layers of the OSI model, we may use a multitude of these approaches. Some of these things we may discuss in some of the upcoming lessons as well. So the main thing to remember is public key systems have been in existence for a long time, and they have become one of the most important part of securing the internet and online based communications. So starting from basic website to web server communications, web services, from application to application in IoT based applications. So there are various places where you may utilize public key systems and various implementations of public key systems. And that is one of the reasons we also need to think about different public cryptography systems like RSA and LGAML, and what are some of the advantages of one or the other, because some of them will have certain requirements. Some of them are more easily implemented on hardware level systems. Some of them are more suited for low powered systems. Again, it is not just computers and servers that are talking, various types of devices that may need to talk with public key cryptography. So we will discuss about some of those things as well in the future. We will also talk about things like digital signatures as a way of using one of the major ways that we would use public key cipher systems. We will talk about authentication mechanisms, message authentication codes, and key exchanges and things like that. Also, we will discuss in the coming weeks. So those are the main sort of topics that we will discuss in the rest of this course. And as always, if you have any questions, feel free to post them on LMS, or feel free to reach out to me through any of your usual communication channels. And until next time, thank you for joining in today's lesson, and goodbye.